So first of all, let's just recap what we mean by waves in any way, in any sense. So if we plus, okay, I forgot we had our frequency really, really low. Let's put it around about something like that. Let's get it, yeah, let's get like that, 1.5 hertz. Okay, let's play. So it's on slow motion. Now, as you can see, the energy is moving gradually to the right. So the direction of energy transfer is from left to right, whereas the oscillation is up and down. And so the way that those two directions relate to each other is that they are perpendicular to each other. So just briefly recap on that. The frequency of 1.5 hertz means that it goes up and down 1.5 times a second. So 1.5 times a second it would go down. If it went down, so after 2 seconds, it would go up 3 times. Okay, each second it goes up 1.5 times. So 3 seconds it would go up twice. The amplitude is how much is disturbed from its original point. So if I got a ruler here and I got it just right, we should see that up to its maximum point is about 0.8 centimeters. So that's what the amplitude means. We always do it from the middle point because that's where, if we move the amplitude down to 0, that's where the line would be if there was no wave moving at all. Let's move the amplitude back up again and press play. And we can also see that the if I were to increase the frequency, the wavelength gets smaller. If you think about it, that's no surprise because the wave is still moving at the same speed, but this thing is moving up and down more quickly, which means in the same distance that the wave has traveled, it's managed to get more waves in that distance, and so the waves would have to squash up. We can measure the wavelength by the distance between any two identical points, so we could go from crest to crest, trough to trough, or anywhere else. So in this case, let's go from crest to crest because it's usually the easiest thing to do, and it looks a little bit over 2.2, maybe let's go 2.25 centimeters. That's the wavelength. Now, if we compare that with where are we going? This one. We can't see the actual wave anymore, but we're saying that wavelength is 440 nanometers. Now, nanometer is extremely tiny. It's basically it's a millionth of a millimeter. Okay, so you can fit 1 million nanometers inside 1 millimeter. If you know what standard form is, then it's 10 to the minus, or technically I should do 1 times 10 to the minus 9 meters. So very, very, very tiny. But the main thing we're interested in is how the wavelength changes the color of the light. So we want to, so let's say blue is the kind of shorter wavelengths. So I guess we could do that. Let's just grab my mouse thing. Okay, and then if I move it up, I'm going to talk about in this video, I'm going to talk about how hexadecimal relates to it. So I'm going to involve a little bit of hexadecimal in here. I move this up. I think we rounded, was it 510? 510, let's try that. Yes, I remembered it. So you can see now, yeah, we'll talk about that in a moment. So basically this is green now. This is, so green is a little bit high. So that was what was it? I've forgotten. It was 440, wasn't it? Yeah. 440 nanometers. And this is 510 nanometers. I'm just going to double check that was 440. I just want to, yeah. So 440. Yeah, 440. And I'm pretty sure the 700 is red. Yeah, good. And also you can get all the other colors by putting it somewhere in between those, okay? So red is 700 nanometers. So drew the wave up here before, didn't I? So I have to, a bit messy, but slightly longer is green, and even longer is red. Okay. So notice that we've got down here all these confusing colours, these confusing numbers and letters and so on. So let's try to understand what all this means. Well, we have the letters RGB, red, green, blue. That's what it stands for. So this R is basically saying, I kind of did it in the opposite order of what we've got down here, but anyway, it's backwards, right? So red is at one end, green's in the middle, blue's on the left, is for shorter wavelengths. So these numbers here are telling us the brightness. Now the maximum brightness is 255. We'll try to understand why it's that strange number in a moment. And then this one here would be the green. So we've got no green at the moment. Well, I need to explain also, what do we mean by we've got no green? Of course we've got no green, it's all red. But it seems that you can, when you actually make these other colours, you can actually have a combination of different colours to make, say, for example, orange. I'll talk about why that is in a moment too. First of all, though, let's understand what these. We understand that. We understand just 255. Well, 159 is less than 255. 0 is obviously 0. So there is no blue light within this. It seems that we can mix these different colours to produce all the different other colours. By mixing all these up, you get all the different colours of the rainbow, right? So, I just got it bang on red, 700 nanometers. So we want to understand, what does this FF mean here? So let's just think about how we count. We take for granted how we count, but basically let's just make it, let's just focus on it for a moment. So if I'm counting something, I've got nothing of that thing, then we would say, well, there's 0. We write the number 0. And as I count up 1, 2, 3, 4, 5, 6, 7, 8, 9. Once I wanted to add, so I've got like 9 apples, for example, and I write down this digit, this symbol for representing the 9 apples. When I want to add an apple, the symbol, I've run out of symbols. I have to reuse some of these symbols. So I write 10, for example, and then I just write another 1, and I write 1 and 0 for 10, 2 1s for 11, and so on. Okay. So we're used to that, but if we really think about what we're writing here, if I write something like 1 5, what I mean is that we have 1 10 and we have 5 1s. So we can go 1 times 10 is obviously 10, 5 times 1 is 5, so 1 plus 5, well, that's 15. So 35 would be 3 10s and 5 1s, so 30 plus 5, 35. That's hardly seems to make any sense to even talk about that, but it's worth mentioning because when we talk about the other way of, well, one other possible way of counting, which is hexadecimal. We have a decimal system. What we use is a decimal system, which means the deci comes from the number 10 in some other language. I can't remember which language, possibly Latin. And the hexadecimal, what that does is it has 16 digits. So they have the same digits as us. So when they start counting, anybody who uses hexadecimal, basically programmers, they will start counting. When they get to here, they actually have more symbols than us. So they don't need to reuse some of those. Their next symbol, they just use the letter A. So A means 10, B means 11, C is 12, D is 13, E is 14 and F is 15. Now they have used up all their digits. That's 16 digits. If they wanted to write the next digit, they would have to write 1, 0, which doesn't mean 10, it means 16. Why does it mean 16? Because the first digit in hexadecimal doesn't mean the number of tens like ours does, it means the number of 16s, because that means 16. There are 1 16s and 0 1s. So let's think about what would FF mean. Well, FF would mean that there are, well, what is F? F is 15. So there are 15, and the first digit is the number of 16s. So there are 15 16s, and the next digit is the number of 1s, and there are 15 1s. So basically FF would be 15 times 16 plus this 15 times 1, which is just 15, of course. So on your calculator, you do 15 times 16 gives me 240, then you plus the 15 and you get 255. So this is translating hexadecimal FF into decimal 255. They both mean the same thing. They're just using what we call a different base. The number systems have a different base. Ours have base 10, hexadecimal is base 16. And you could also have a bit of fun and play around with other types of number systems. There are other number systems that exist. The reason why we use base 10 is because we've got 10 fingers. That's the reason. When we started counting, when we try to count, oh, do you have more something than me? We might count on our fingers. And so we used decimal system to count that far. If you compare that with, okay, so what was I going to say next? I was going to say binary. Binary only has 2 digits, 0 and 1. So 0 is just 0, 1 is 1. Now we've run out. How do I write the number 2? I would have to start again. 1, 0. That means 2. 3 would be 1, 1. Okay. This is how we count in binary. All right. But you could do any system you like. Anyway, so basically you can. So this is your. So whenever you see these numbers, a 6-digit hex code for your work out what color something is, then it's telling you how bright. And I just realized one other thing I haven't explained yet. How bright the red, green, and blue LEDs are. So these, your screen is made out of millions of LEDs. That's when we say how many megapixels has it got. Each pixel has got 3 different LEDs on it, red, green, and a blue LED. And the brightness of these LEDs is represented in this hex code here. So if I just drag this down here like that, now we can see that red is still at maximum, which translates up here as well. The the green, is represented by E9, which is at 233, and the blue is still 0, 0, 0, right? So that's what hex codes mean. As I said, these colors can be made by combining these three colors here. So let's look at a couple more things now. This way, I didn't explain the lesson, but I'll briefly explain it now. If I go to this color vision and turn it on, when I shine yellow light, well, this person sees yellow light. No surprise there, right? But what we can do, as I said, is you can make any color by mixing the red, green, and blue. So I shine red light and she sees red. Yeah, I don't know if it's a she or a he. Green light sees green, and so on. What would happen if I mix red and green? They see yellow. So if I were to, I don't know if I'm going to be able to do it on this thing here, but if I was able to get color, in fact, you can see it's around about yellow now, and the red and the green are roughly the same brightness. Okay, so so that's basically. I'm not going to talk too much about why that is. It's very interesting why that happens. It's to do with the structure of our eye. We've got cones and rods. The cones are the things that no, is it rods? I think no, it's the cones that I think are the ones that detect color, and they're sensitive to different wavelengths. But anyway, the point is you can mix red, green, and blue to make any other color you want. And then you'd get all those different colors, whatever they are. Now let's just look at this one. This is a pretty cool little simulation as well. This is an image of an LCD screen. So if we were to, if we go down to here, at the moment, what we didn't do in the previous one is we were able to turn all the brightnesses up to 255. So we weren't able to do this, sorry. But if you do, you get white light. If I turn the blue down, as we saw a second ago, we get yellow light. Oh, okay. So we've got yellow light in this case. Now, as I said, we've got the LEDs, the red ones and green ones are turned up to max. And when we combine those, strangely enough, we see yellow light. There is such thing as pure yellow light, where the wavelength is of yellow light, but you can also make, I suppose, fake yellow light, which is basically all the yellow you'll ever see on your computer screen, phone, TV, or whatever, any other electronic device, because they're made out of these. If we zoom in on this simulation, we can start to see the pixels, and we zoom all the way in, you can see that they're made out of 3 types of pixels, and the ones in black, well, they'll be the blue ones. If I turn the blue up, we have that. So there's all the red, green, and blue pixels zoomed right in. You can do this yourself with, if you've got the right tools. You just get a magnifying glass maybe, and I don't know, depending on the resolution. Or you look, if I look at my monitor really, really closely, I can sort of just make out in the white background the different pixels, and might even be able to see that there are red, green, and blue pixels there. But so if I zoom back out again, and I can still just see red, green, and blue, but at some point starts to just generally become a sort of greyish colour, and that's just because those black imaginary boundaries are drawn there. Keep zooming out, the boundaries go away, and I have white light. Okay, anyway, so yeah, I'll stop there. I hope that was interesting and useful.